Everyone sees my screen?
Yes.
Okay, good. Yeah, so we are saying that function which satisfies the Laplace equation is called a harmonic function. So in brief, actually, you can simply say that a function which satisfies the Laplace equation is known as a harmonic function. So it can either be in 2D or 3D. And remember, harmonic functions are the Laplace equation in 2D is if a function is phi, partial squared phi, partial x squared, plus partial squared phi, partial y squared, equal to 0. This is in 2D. Or partial squared phi, partial x squared plus partial squared phi, partial y squared plus partial squared phi, partial z squared equals to 0. This will be in 3D. This is what we call the Laplace equation or equations. So if the problem or the function you're dealing with is in 2D, then this is what you need to prove. If the function you're dealing with is in 3D, then this is what you need to prove. So example, show that the following functions are harmonic. So the first one is u, which depends on x and y, is given by x squared minus y squared plus 2x. So what we need to, so this function is in which dimension, 2 or 3? Function at hand, is it in 2 dimension or 3? What makes it to be in 3 dimensions? What makes it to be in 3 dimensions? What makes it to say that u is in 3 dimensions? What makes you say u is in 3 dimensions? Is u in 3 dimension or 2 dimension? Hmm? Is U in 2 or 3 dimension? Is U in 2 or 3 dimension? Come on. Is U in 2 or 3 dimension?
It's in 3 dimension.
The reason why you say 3 dimension? Two X. If it's Z, I'll put if it's Z, I'll do this just to make the distinction. Yeah, this is in 2D because it's only depending on X and Y, okay? So then now we show that, so solution, we show that partial squared U, partial X squared plus partial squared U, partial Y squared equals to 0. This is actually what we call the Laplace equation. And the function here is U. So to get second derivatives, you must get first derivatives. So what is partial U, partial X? So if you have problems on how to do derivatives, you may not go far. Partial U, partial X? 2x plus 2. And then partial squared U, partial X squared means you differentiate the first derivative. The same as partial X of the previous answer, which is just 2, okay? And then partial U, partial Y. Partial U, partial Y. Negative 2y. So which implies partial squared U, partial Y squared will be negative 2. Then clearly, partial squared U, partial X squared plus partial squared U, partial Y squared is 2 plus minus 2, which is 0. So therefore, the function U equals to X squared minus Y squared plus 2x is harmonic. Then 2, V is a function 2 e raised to power x cos of y. So for this one also, we show that partial squared v partial x squared plus partial squared v partial y squared is 0. Simply to say that v satisfies Laplace equation. So what is partial v partial x? partial v partial x. So we differentiate this function with respect to x. We know.
E power x.
To e power x cos y.
Cos y.
And then the second derivative. Will be 2 e power x cos y. It's a very interesting function because actually when you differentiate, you get the same thing. Okay. Yeah, for with respect to x. And then let's see. With respect to y, correct? Which means then the second partial derivative with respect to y. To e still negative. Because when you differentiate sine y, you get just sine y, but there's a negative sign, okay? Are you seeing where the negative comes from? Yeah, because the derivative of sine function is positive cosine, but the function already had a minus sign in the first case. So that's why you have that. So clearly, partial squared v partial x squared plus partial squared v partial y squared is 2 e raised power x cos y plus minus 2 e raised power x cos y. And even a blind person can see that the sum is 0. Then 3, to one free time, also confirm that when I have a function, say phi of xy given by ln of x squared plus y squared is also harmonic, and also show that if I have the function, say phi of xy given by x over x squared plus y squared is also harmonic. If you get stuck, the solutions actually are in my other previous class lectures, so you can always check out. So lastly, there's what we call conjugate harmonic functions. So two functions are said to be conjugate harmonic if they satisfy the Cauchy-Riemann equations and are themselves harmonic. So when two functions are harmonic, and at the same time they satisfy the Cauchy-Riemann equations, then such functions are called conjugate harmonic. So an example, check whether the following pairs of functions are harmonic, are conjugate harmonic. So the first one is u of xy given by 3 into x squared minus y squared, and v is a function 3x squared y minus y cubed. So remember, the first test is to show that each of them is harmonic, and then show that the two functions satisfy the Cauchy-Riemann equations. So solution, first, we show that each function is harmonic, i.e. test whether partial squared u partial x squared plus partial squared u partial y squared equals to 0, and partial squared v partial x squared plus partial squared v partial y squared equals to 0. I want you to quickly confirm for me, is u harmonic? Check whether u is harmonic. Check whether u is harmonic. Is u harmonic?
Yes, it's harmonic.
So what is the second partial derivative of u with respect to x? 6, and then the other one is minus 6. So then that's what tells us that the u function is harmonic. So this is how he's actually obtaining the answer, that u is given as 3 into x squared minus y squared, which you can write it as 3x squared minus 3y squared. So partial u partial x will give you 6x, which means partial squared u partial x squared. When you differentiate 6x with respect to x, you get 6. And then partial u partial y is minus 6y, which means partial squared u partial y squared is minus 6. And clearly, if you add the two, you get 6 plus minus 6, which is actually 0. So therefore, u is harmonic. Now, can you also test for v? Is v harmonic? So do the same process. Get partial u partial v partial x, partial squared v partial x squared, and similarly for y.
So can you scroll up to?
Okay, so the other one is 3x squared y minus y cubed. Does v also satisfy conditions for being harmonic? Yes or no? Is v harmonic?
Yes.
Should be. So because v is given by 3x squared y minus y cubed, so partial v partial x is given by partial v partial x.
Six XY.
6xy. So which means the second partial of v with respect to x is 6y. And then partial v partial y minus 3y squared. So which means the second partial derivative with respect to y will be y, correct. So then clearly, partial squared v partial x squared plus partial squared v partial y squared is 6y plus or minus 6y, which is 0. So therefore, v is harmonic. So both v and u are harmonic, but let's see, are they conjugate harmonic? So step 2, check if u and v satisfies the CREs. So this means that we check that partial u partial x equals to partial v partial y, and partial u partial y equals to negative partial v partial x. So if that's the condition, if those two conditions are satisfied, then we conclude that the two functions are conjugate harmonic. So from the u function, what was our u partial x?
6x.
6x. And then partial v partial y? Minus 3? Minus 3y squared. So when you are computing was this partial v partial y correctly computed here? In the previous step. So when you differentiate this with respect to y, is the answer just minus 6 minus 3 y squared? If you differentiate this function with respect to y. Remember the first term also has a y. So it should be 3x squared minus 3y squared. Okay? At this point. When you are computing there's a 3x. I think that in the first term, there's also a y in the first term. What v is given by 3x squared y minus y cubed. So when you differentiate this with respect to y, this part and this part of them, both of them have y. So the first part is 3x squared. But we are just lucky that it's a coincidence that that part doesn't affect the final answer for the second partial derivative, okay?
Yes.
Yeah, so it's just that we are lucky that we're able to do that. But then this term was omitted, so it's supposed to be 3x squared minus 3y squared. So the partial v partial y is minus, I have 3x squared minus 3y squared. And actually, you can see that partial u partial x is not the same as partial v partial y. So one of the conditions is already not satisfied. So obviously, the function can never be conjugate harmonic. Or if you are even to get the second condition, what is partial u partial y? Partial u partial y?
6y.
Minus 6y. And then partial v partial x. You get?
6xy.
6xy. You see also this one, partial u partial y is not the same as negative partial v partial x. So then, since partial u partial x is not equals to partial v partial y, and partial u partial y is not equals to negative partial v partial x, so this is simply to mean CR's are not satisfied, then u and v are not conjugate harmonic functions. So this example alone shows tells us that it is possible for two functions to be independently harmonic, but then fail to be conjugate harmonic. So at your own free time, also check for these other pairs. If you have u equals to x and v equals to minus y, then if you have u equals to e power x plus y plus 1, and you have v as 1 plus e power x sine y, if you have u as x over x squared plus y squared, and we have v as negative y over x squared plus y squared. And lastly, if you have u as x squared minus y squared, and v as y over x squared plus y squared. And then also prove this theorem that if f of z is u plus iv is an analytic function, then u and v are both harmonic. So prove that is that. So all the answers to this problem actually are in my previous classes. So get some time and check out. And also check and write, say, 2 examples on how to find conjugate harmonic functions when given one of the 2 functions. So that'll be the best point to stop. So do that work using the books I shared and the previous link that I shared in my previous classes. So next week we'll be doing the CAT 1. You tell me whether you want it to be online or physical next week on Friday.